Hello everyone, my name is Seyedkeivan Nateghi, PhD student from Silesian University of Technology, and I'm presenting the outcome of my study titled Life Cycle Assessment of Airborne Infection Control Strategies in Classrooms. During pandemics, the importance of infection control strategies has highlighted. While some methods have been adopted, most decisions are made without considering the environmental impact. This study aims to fill this gap. The main goal of this work is to evaluate the environmental impact of different infection control strategies. We focused on air cleaners, disposable masks, and a novel solution combining personal exhaust ventilation and physical barriers, or in short, PB plus PE. This design includes plexiglass partitions, enclose a desk to accumulate the exhaled air and then capture this by an exhaust fan. To compare environmental impact of different strategies fairly, we define a functional unit as the use of each strategy in a classroom of 30 students operating for 6 hours a day, 5 days a week, over one academic year, and then scale all results to a 10-year period, which is the expected lifetime of the air cleaners. We also assumed 2 devices for air cleaners based on the area of classrooms. Single use of mask for each student every day, and one system of PB plus PE for each desk, resulting in 15 systems in classrooms. The system boundary is cradle to grave. It includes raw material extraction, production, use phase, and end-of-life processes. Transport impacts were excluded due to their minor contribution and high uncertainty. During use phase, air cleaner consumes electricity and filter. Disposable mask has nothing in this stage, and PB plus PE has electricity. The way of disposal for each strategy was selected based on references. We then created a life cycle inventory of materials for each strategy. For example, air cleaners involve various plastics, metals, electronics, and filters. Masks involve large amount of polypropylene, aluminum, and packaging materials. PB plus PE require plexiglass, aluminum, 3D printed PLA, and ducts. The inventories from mask and air cleaner were obtained from references, and PB plus PE was from our own data. We designed this in our laboratory. We modeled the challenge using OpenLCA software, and the impact assessment method is based on EF3 method following European Commission guidelines. The total impact includes production, 10 years use phase, and end-of-life disposal. The result of raw material processing are shown here as hotspot analysis for each strategy. First one is air cleaner. Air cleaners show high environmental burdens from electronic components, especially in human toxicity and ozone depletion. For mask, fossil-based materials like polypropylene are the most impactful, especially in terms of water use and eutrophication. PB plus PE systems have concentrated environmental impact due to PMMA or plexiglass use. The use phase was assessed for 10 years. Disposable masks were not considered as during use phase don't have any impact. The table summarizes the calculated impact categories for air cleaners and the PB plus PE system based on their electricity consumption. For air cleaners, electricity consumption of 680 kWh resulted in significant contributions to all impact categories. In PB plus PE system, the higher electricity demand of 1,900 kWh amplified its environmental impacts across all categories compared to air cleaners. We also did a sensitivity analysis to test how changes in materials or energy use would affect results. Main input flows or crucial inventories were selected. Parameters were perturbed by minus plus 2%. For each impact category, the maximum sensitivity is marked in red and the minimum in dark green cells. Electricity had highest impact on 7 categories, electronic components also on 4 categories, polypropylene on 3, and PMMA on 2 of them. To provide a final comparison, a single score was applied, integrating all impact categories like climate change, resource use, and others through normalization and weighting into a total environmental burdens measure, PT or points, which is dimensionless. This considers relative contribution of system to overall environmental impact, compared to a reference scenario which is annual environmental impact of an average European citizen. The result shown in figure. The high environmental impact of single-use masks over the long term suggests that alternative protective solutions. Although air cleaner has the lowest environmental impact, PB plus PE is the most effective strategy in terms of infection control. In conclusion, disposable masks have the highest environmental burden due to single use, so it's not recommended to use in classrooms. While air cleaners have the lowest environmental impact, their effectiveness alone may not be enough to control infection risk. Personal exhaust ventilation with barriers with relatively low environmental impact is most effective strategies to control infection. So we can recommend PB plus PE as a balanced and eco-friendly strategy. Thank you for your attention.